Now we're going to explore a graphical representation of the derivative as a function. And we're going to start by looking at one of the functions that we looked at previously. Let's let f of x equal x cubed. And if you would like, it might be a good idea to open up GeoGebra so that you can follow along as well. So I've just inputted this function, and if we were to look at this function, you could sort of estimate what the derivative is at each point by estimating the slope of the tangent line along each of these places. Let's be a little more accurate. We're going to go up to our menu and click the point, and we're going to add a point A onto our line here, our function. And now we want to add a tangent line that goes through this point A. And the best way to do that, rather than doing something complex, we can go up here at the top menu bar. There's this option called tangents. And if I go down, I can click here where it says tangents. And then I click on the point A to tell it to go through the point A. And then I click on the graph. And a line appears. And notice if I go to the arrow, I can move my point A and it will shift the line, the tangent line. I'm going to highlight the tangent line. I'm going to turn it red by right-clicking, going to Object Properties, and changing it to this red color. Makes it a little easier to distinguish between the function x cubed and this line, the tangent line. Now it's easier to see what the slope looks like. So let's go to where we have an x value of 1. So our input is 1. Our output gives us, on the function line, is this line. And then we want to examine what happens, what is the slope at this point. The way that we can tell what the slope is by looking at the equation of our line. We here see y equals 3x minus 2 is the equation of our tangent line. So that means that the slope of the tangent line in this case is 3. That's the coefficient in front of the x. And so that means that our derivative when x equals 1 is 3. I'm going to add a spreadsheet view so that we can keep track of some of our notes. So this is saying that when I have an input of x, I have a slope. Oh, sorry. I don't actually, okay. So we said that when our x value was 1, our slope value was equal to 3. Now let's visually estimate what happens as I keep moving my point along here. So when our x value is 0, we can see that our line becomes flat and our slope is 0. And we can also see that as we travel in the negative direction, as our x value goes down to -1, our slope is also equal to +3, that we have symmetry in this graph, -1, 3. And if I wanted to, I could start plotting all of these points, right? I could plot these along the x-axis so that when I input a -1, I get out the slope value, which is 3. And then I could plot 0, 0, which would be a point here. I could also plot a point 1, 3, which would be a point up here. And if I plotted all of those values, that would trace out, for each input of x, it would give me the output that's the derivative of this curve at that point. Instead of plotting this all out by a table, however, let's let GeoGebra do it faster for us by creating a new function. So let's create a point B. We're going to set our point B equal to, and this is my point notation. There's a weird notation. I want it to have the same x value as a, because as I move my a along, I want my point B along to move with it. And the notation for that is x square bracket of capital A, because capital A is the name of my point. And then I want its output to be the slope of my tangent line, slope of lowercase a is the name of that line. So hopefully, I have too many brackets there. There we go. Uh-oh, I have too many brackets. There we go. So what is this saying? This is saying that when I plug in an x value of -1, we see that our tangent line is here in red, and the slope of that tangent line is way up at 3. And so that means that if b is giving us an output of our slope, our output is 3. And as I move this point A along, we see that when we're right at x equals 0, the slope is 0. When my x value is 1, the slope is 3, and the slope gets bigger and bigger as my x values get bigger and bigger. And how can I track this? We're going to do something clever. First I want to change the color of my point B to something that's easy to see. We're going to do a nice blue color. And then I'm also going to add a trace. So now we can see the path of B as our A moves. So starting from here, as my A value shifts, we see that our B value shifts with it. And as our A value continues to shift, our B value shifts as well. And by tracing out this curve, we see that the pattern that B traces out is that of a parabola, which is exactly what we saw before, that if I were to graph the derivative of my x cubed function, I would get out a modified x squared function. It's actually the 3x squared function, which means that it's been squished vertically together a little bit. Let's explore a different function. Let's go ahead and change this function. I'll just go right in here to edit it. And I want to explore the function e to the x. That's another function that we talked about. Let's clear all this. So a fast way to clear things is to just change your view by moving the graphics around. But I'm leaving everything else in place. That way I don't have to remake my tangent line. So at this point, I'm looking, my point B seems to be right on top of my point A. It's hard to distinguish the two. And really that's because for the e to the x curve, the slope is exactly its output value at every single point, which is unique only to this particular curve. And we can see that, for example, when x equals 1, our output is e, which is 2.7 stuff, and the slope is exactly equal to 2.7 as well. That's why the slope of the original curve is exactly equal to the height of the derivative curve. And let's look at one more function. Let's look at a messy polynomial function like x to the 4th minus 3x squared plus x minus 1. So this is some loopy crazy function. We're going to move around a little bit to get rid of our view. And just looking at this function, we can guess what we think the derivative might look like. Notice that at this point in the function, we want our derivative curve to be 0. So we would hope that, for example, as I move my a, we would want our derivative to be 0. Oops, I need to be on the arrow so I don't drag the thing. Arrow. So I'm going to drag my point A, and we notice that as point A moves here, our B value goes through 0 because right here our slope is 0. We also have a slope of 0 right here, so we would hope that our B values are 0 through there as well. And then finally our B value will be 0 again down here. We see another place where our B curve is 0. And we're going to have an ongoing negative slope through here. So just by evaluating what's going on in our original function, we can get some picture of what's going on in our derivative function. Really all that I can tell is where is my derivative function going to be equal to 0? That's this flat part of the curve means our derivative function is at 0. This flat part of the curve means our derivative function is at 0. And this flat part of the curve means our derivative function is 0. And then between those places, we can tell whether our function is positive or negative. Here we have a negative slope, so our derivative is taking on negative values. Here we have a positive slope. Even though the slope goes from being really positive to less positive, through this whole stretch, notice that we have a really steep and then it flattens out and it gets flat. All of those are positive values, and that's what's indicated by these positive blue points up here. The negative blue points are indicating that we have negative slope values through here. So this is just one exploration of looking at the derivative as a function graphically.